if we choose to solve this system using the elimination method, how does that change your strategy? What do you want to do first in this example to use elimination instead of substitution? What's your first move? Yeah, Paul. Multiply. Multiply what by what?
Top equation.
Okay. Multiply it by how much?
3.
All right. So, first of all, using the elimination method, your first step is to multiply an entire equation, or maybe both entire equations, depending on the circumstances. And Paul here is saying, let's multiply this first equation by 3. And so, of course, I'm going to be interested in the question, why 3? What does multiplying the first equation by 3 accomplish? Say again. Yeah, I'm going to change that in a second. But 3, some flavor of 3 is a good choice. Because what are we really setting up to do here? We're setting up to eliminate one of the variables, and we're eliminating it in a different way here than we did when we used the substitution method. Right? If I multiply the first equation by 3, which variable does it look like I'm setting up to eliminate? X. Right? Because what I've accomplished is I've now made it so that the coefficients of x in both equations are the same. I have a 3x in the first equation, I have a 3x in the second equation. And that, in principle, should make it possible for me to eliminate the x by combining these two equations together, left-hand side and right-hand side. But in order to combine these two equations together, I have two choices. I can either add one equation to the other, and get a third equation, which must also be true, or I can subtract one equation from the other and get a third equation, which must also be true. So I have the option here of either putting a big giant plus sign here and adding these two equations together, which if I did that, I would end up with 6x plus 7y equals 10, which doesn't seem helpful because I haven't gotten rid of a variable. So what should I do instead? If I want to eliminate the x, because my coefficients of x are exactly identical in the two equations, to eliminate x, what I need to do is subtract. If I subtract 3x from 3x, how many x's do I end up with? Yeah, none. And then 6y minus y, 5y. And then here's a great place to make a sign error. What's 15 minus negative 5?
Well, it won't.
Yeah, so that ends up being 20. So I'm hearing some of you kind of cluck your tongues a little bit at how I'm doing this, which I completely understand. Because what I did here is subtract these two equations together. And that's kind of a recipe for disaster if you're prone to making sign errors. So I'll show you kind of a different way to approach this in a second. But both ways are going to lead us to the same equation, which no longer has x's in it. 5y is equal to 20. And then to solve 5y is equal to 20, I'll just divide by 5 to get y equals 4, which was the same value of y that we found when we solved this system of equations using substitution. And once you know that y is equal to 4, how do you find x? Yeah, just plug it back in. Again, you can plug it back into either equation, whichever one you happen to like better. So just for fun, I'm going to use the second equation here. 3x plus y is equal to negative 5. And since we know that y is equal to 4, we can put a 4 in place of y. Equals negative 5. And then we just need to solve this equation for x, which we can do by subtracting 4. And getting 3x equals negative 9. And then dividing by 3 to get x equals negative 3, which again was the same value of x that we got when we solved the system using substitution. So those are the main contours of using the elimination method. We need to, very often, manipulate the original equations. In this case, we got away with manipulating only the first one, but manipulate them in such a way that the coefficients of one of the variables makes it so that adding or subtracting the equations from one another will eliminate that variable. Then once that variable has been eliminated, we get a second equation which only involves the other variable, which we can solve, and then plug that answer back into any of the original equations to find the other. Now, how do you avoid making sign errors in doing all of this? I'm going to follow the advice that I heard from several of you while we were just talking about this. And instead of choosing to multiply that first equation by 3, which had the effect of making the coefficients of x exactly equal to one another, if I want to be as careful as possible about signs, I might instead choose to multiply the first equation by -3. Because that is going to have the effect of making the coefficients of x not equal, but equal and opposite. I'll then get minus 6y here. I'll get minus 15 over here. Right? But the virtue of that is that we're no longer needing to do any adding and subtracting of negative numbers. Instead, all we end up needing to do then, to cancel the x, is add these equations to one another, wherein the x's once again cancel, but then I'm going to end up with negative 5y, right, and negative 20 over on this side. But it's a lot easier to avoid sign errors when you're adding numbers together rather than when you have to subtract numbers and one of them is negative, one or more of them is negative. So very often when people use the elimination method, they put the focus on making the coefficients equal and opposite rather than making them equal and then having to subtract, which makes a sign error more likely.